And then we don't have class on Monday because Monday's a holiday. Yeah, I'll have office hours tomorrow morning if you need anything. The homework's due Wednesday. Monday's a holiday. Tuesday I'll have office hours. Wednesday will be our last class before the test. Yes?
I'll just ask one question.
Sure.
Have a doubt on how protocols are because most of the protocols I skip Dr. Stated the following sentence, but most of the sentence, like I have read about it on the book, but not necessarily what's told said by her. Like for example, some scientists said the goal we have on the protocol, so I'm not sure if you expect us, since it's her who wrote the book, obviously. I'm not sure if you expect us to draw on those cases or almost if it's not her.
Yeah, so it's just, so you can read that as saying that it from her book, basically. Yeah, so if she's quoting someone or putting something forward that she believes in, then that would apply when it says according to Dr. Feldman. If she's put something forward that she doesn't believe in, then that would be false, right? If it was according to her. And the reason that all those start with according to is because, like a lot of things in science, you're going to have scientists that disagree with Dr. Feldman. So even though she puts forward her ideas and justifies them in her book, I didn't want you to just, you may disagree with something that she says, but I don't want you to get the question wrong. So it's basically, what is she saying? What is she saying? Okay. At the moment of vision, the eyes see nothing. I think by now, hopefully you guys understand this, this part. If not, I think it's partly on your homework, that the brain is vision. The eyes are part of vision, part of what feeds vision. You should understand fairly well now chapters 1 and chapters 2, plus like the introduction of the book. The homework's going to relate to that, and it'll be covered on the exam. I'm not going to talk about the book really in class other than to answer questions, because I think the book you can read and understand it. So, and if you don't, then come to my office hours. Who's the book dedicated to? Huh? Sophia, very good. It's a different Sophia. Okay, we're hopping through sensors. Today we're going to talk about light. Last time we talked about sound. You're going to see there's some pretty cool similarities between sound and light, even though in some cases they're very different. We can think of them and work with them in ways that are fairly similar. And then hopefully we'll get into smell and taste today. So eyesight refers to the attributes and the functions of the organic components involved in the vision system, which means that when we're talking about eyesight, we're really talking about what the eyeball and the things closely affiliated with the eyeball are doing. When we talk about vision, we're talking about the interpretation of what's coming in from those electrical signals, which we know vision involves both subconscious processes and conscious processes. That's why in the McGurk effect, vision was so powerful in the subconscious processes that it caused you to hear things in your head that weren't actually being said in the room around you. This is an eyeball. And this eyeball collects electromagnetic radiation, light, and directs it through that lens, which you can see there is the blue thing. Interestingly enough, the optics of the eyeball are like a common lens in the sense that they flip the object on the back of the eyeball, the back of the eyeball being called the retina. Why don't we see things upside down? Or is the world upside down and we see it right side up? I'm going to suggest to you that even if someday someone were to add a different lens, like let's say you put an inverter lens in front of your eyeglasses to flip actually everything, that although you would be confused for a little bit of time, at some point, I believe that your brain would start seeing things right side, correct side up.
Actually, there's some glasses that they have like crystal. Yeah, crystal. It makes you see everything upside down. And I heard that there's been a person that used like got accustomed to the glasses and actually like inverted he started to see everything that was supposed to be upside down. He started to see it like, upside up.
Oh, right.
The right.
I didn't know it, but it validates my theory. And that's also, if you remember when we were talking about sound, that people can learn to hear things, if you will, or make sense of things, even if what's coming in is very different than what they were accustomed to. So that's the brain sort of reprogramming itself at the subconscious level to make sense of the world around it. Because the brain has to not just make sense of what's coming in through the eyes, but like in the McGurk effect, has to make sense of that together with what's coming in from the ears, right? If you watch a concert or watching a show and there's lip syncing going on, your brain kind of identifies that and says something's off here, right? Because it's expecting the mouthing, what it's seeing through the eyeballs to match up with what it's hearing. Okay. So again, I'm going to put forward here that this is very maybe crystal clear when we can see things like the McGurk effect associated with eyesight and sound, which we rely on so heavily. But I'm going to suggest to you it's also there when we talk about things like smell, taste, touch, and our internal senses that are very interrelated to our emotions. And so we make sense of all of that all together in our brains. So the lens directs it to the retina. There's a transformation there into electrical impulses, and those get to the brain, and that's where you start making sense of what's happening. We can zoom in here a little bit. In here we have rods and cones. You remember from our multi-layer, I think it's 7-layer model, that there is a layer that's associated with receptors. And here are some examples of receptors that are involved in your eyesight, and those are cones and rods. Cones, there are 3 different types of cones: a red cone, a green cone, and a blue cone, RGB. And those cones are labeled that because they are more, well, I'll tell you why they're not, let me get back to that. They are labeled that. I'm not exactly sure why they're labeled that, and I'll show you that in a little bit, why I hesitate. The cone cells are concentrated and characteristically sensitive to red, green, or blue light, and we'll see what that looks like in a little bit. Basically, what the rods do is they work as very, very sensitive light receptors, but they can't distinguish color. So the rods kick in when there's not a lot of light. So one thing that you can do is right before the sun goes down, where you can still see a tree, look at the tree and see if the tree really looks green or not, or if it just looks like a dark gray or a black even. Now your mind can fill that in and make it look like it's green, but the reality is when there's a little bit of light, your green receptors, which are the cones, aren't sensitive enough to actually activate, and so you can't distinguish color when there's not a lot of light. But your mind can adjust for that. And if it knows it's supposed to be green, it can throw in some concepts to actually color a little bit the leaves green, even though you can't really see the green leaves with your eyes. This is why I hesitated a little bit. Even though they are called blue cones, green cones, and red cones, the red cones are actually much more sensitive. If you can tell by the peak there, this is a plot of retinal response. They're actually much more sensitive to yellow light than they are to red light. And blue cones are actually more sensitive to magenta light. So those dashed lines going down show you where those colors basically line up in the electromagnetic spectrum. And you can see that red cones really aren't very sensitive to red light at all. But on this resolution, you can see that green cones and blue cones aren't sensitive at all to that light. So if you're seeing any red, it's because of the red cones. By the same token, if you're seeing things that are all the way out in the violet, that's actually coming from the blue cones. But if you look at blue light, it's actually a combination of the blue cones and the green cones. Now, let's look at the rods. The rods actually can sense light from the lower end of wavelengths all the way to around 650 nanometers. And what that means is if you don't have enough light to activate your colored cones, the rods are going to kick in. And when those rods kick in, they're going to basically give you a shaded gray, if you will, view of the world for light that's coming in regardless of its wavelength. Here's another way of looking at that. Again, going down, you can see where blue, green, and red are. Notice that your green cones are far more sensitive than your blue and your red cones. That means if you have green light coming in, green photons, you don't have to have as many green photons coming in before you're going to be able to see something that's green. Whereas if it's something that's red or violet, it's got to be something that's much, much brighter for you to see it. The human eye, according to some reference, which I don't know how they prove this, but the human eye can distinguish 10 million colors, approximately 10 million colors. 10 million colors. Here are some of those colors as labeled in English. Let's do a little test here. There's aquamarine. What's that? What's aquamarine in Spanish? Aquamarino? Amber. What's the color amber in Spanish? What? Amber. Okay, cool. What's the color of vermilion? In between red and orange. Chartreuse. Okay. So, question, if you don't know the name for a color, can you see that color? Okay, so if you're comparing colors, you can tell differences. Why are color printers CMYK but displays RGB? So what does that mean? That means when a display, like a projector, it's shining off this whiteboard here, is essentially combining red light, green light, So red light, blue light. There, red, green, and blue. Red, green, and blue light to show all the colors that you're seeing. But printers don't work that way. Printers use CMY, K, C, if you remember from here, is cyan, yellow, and magenta. And what's K? K is black. K is black.
They don't use beads.
Huh?
They don't use the other beads.
They don't use, well, what we're trying to say here really in this comparison is that when you combine colors and you're creating light, then when you're not creating any light, the screen is black. On a piece of paper, which is typically white, when you're combining colors, if you don't combine the colors, if there are no colors that you put on the paper, then it's white. So while you're combining these colors, basically you end up with darker colors. And it turns out that on average, cyan, I always get that one confused, cyan, magenta, and yellow are brighter colors than red, green, and blue. You already know that because I showed you this thing. Right? Your eye's not very good at detecting low levels of blue, and your eye's not really good at detecting low levels of red. So even though you can combine red, green, and blue, by shifting it over, you're able to use colors that your eyes are more sensitive to. And that's important because as you start combining ink, the way it works on paper is that ink is absorbing light. It's not generating light, it's absorbing light. So to create a color, I have to absorb different combinations of colors. And when I do that, it's going to look dark. So how do I get something light and bright? And that's why they use cyan, magenta, and yellow instead of red, green, and blue.
So by combining the cyan and yellow, you get dark in the middle.
Yeah, the K is there because it's really hard to make something really, really dark when you're using these brighter colors and you're putting it on a white piece of paper, basically. So that helps bring things to be darker. So things that happen in every single day we don't really think about there, right? What are the primary colors of the rainbow? If you've been great students and have already read chapters 1 and 2, you may know the answer to this question. That's actually from my camera, from my house. I took the picture of the gold mine on the other side, on the top of that mountain. So presumably, according to Dr. Feldman, if you ask, she would say that this very colorful artistic rendition was done by an American who only thinks that there's 6 colors in a rainbow, because in Russia, there's not blue, light blue and dark blue. In Russia, there's just 2 different words altogether. So it would be like I'm saying, like there's the color lor and the color mez. And I'm referring to light blue and dark blue. So in our concept, blue is blue, and we're thinking about it as light and dark. But what if all our lives, whenever we saw something that we call light blue, someone said that was lor, and whenever we saw something that was dark blue, someone said that that was mez. Well, according to Feldman, that's essentially what happens in Russia. And if that happened, then when you looked at a rainbow, you'd see 7 colors instead of 6. What color is this? Royal blue, indigo, dark blue, light blue, blue. Blue. Or blue is 0000FF. What's that? In hexadecimal HTML 0000FF. Anybody want to guess as to what FF0000 is? Huh? Red. Very good. 00FF00. Excellent. Excellent. So if we go by that, we can actually resolve a lot of colors, not by trying to remember is something royal blue or dark blue or indigo or light blue or Laura or Mez, but just by calling colors what all computer scientists realize is hexadecimal, right? We don't have to worry about the names. We can tell a computer program quite effectively in our friends in our classes that we don't want dark blue, we want 00008B. Dark turquoise 00CED1. So I like to throw a little bit of computer programming and software in here every once in a while. This will be your worst nightmare if you work in disciplines with graphic designers and artists, and you're their computer programmer. You will either become friends or enemies very quickly because they won't be able to understand why what they've done isn't showing up the right way on your in your program or on your screen. Yeah.
Is there a grade with A, grade with B? That would be.
I don't make it up. I don't make it up. But the letters are still the same, so I think that's just a typo. Are they the same color?
With dark gray and gray, it says like A and B.
Yeah, I know in English sometimes you'll see gray spelled both ways, but those are actually the exact same codes. So
it's just like,
I think it's just a mistake on the printer. Unless you see them as being different, which you could. So if you can't name the color, can you see it? And here, you know, I'm alluding to the situation which is a little bit different, which is if you grew up with Laura and Mez, you know, would you see them as just two different shades of blue? Presumably not. So what about when it comes to feelings? So if I'm mad, if someone says I'm mad, does that mean this, whatever it is that I'm feeling, is that the same thing as what you think you're feeling when you're mad? And what if all your life, when you were frustrated, what if throughout your whole life, the people that raised you, whenever you were frustrated, they said you were mad? Why are you mad? So what would you think when you're frustrated? You might think that you're mad, right? Because you learn over time that that feeling that you're feeling of frustration is maybe supposed to be mad. So you can imagine two people different, grown in different households, and it gets even more maddening in the English language because you can be mad when you're crazy. Like you go to your parents and say, hey, I want a raise in my allowance, you know, because of inflation. And in the English language, your parent might say, you're mad, get out of here. Or parent might really be mad or think someone's mad. So for better or for worse, we grow up mostly learning about our emotions and the words that go with our emotions that are subjective already to start with, outside of a formal environment. And they're subjective, which means that whatever you're feeling, you're going to associate presumably with some subset of all these words. If your parents were English or Spanish teachers, and aware of this sort of thing, they might help you by, whenever you're feeling something, trying to spend some time to try to understand, have you describe what it is you're feeling, and then try to help you identify what the right word is for that. So according to Feldman, if you had parents or the people that raised you very, very literate in the perhaps thousands of words for emotions that you might feel, they might be able to actually help you manage or work with or leverage your emotions throughout your life, because when you're feeling something, you would be able, presumably, to just say, you know what, I'm feeling hungry, instead of thinking you're feeling sad or mad because you're hungry. Right? So the idea is, understand what it is that you're feeling, which is these internal sensors, which we're not going to talk about today. But understand what that is and try to put a word around it that best exemplifies what it is that you're feeling. So yeah. Now this is a color chart. If you memorize that, you'll recognize that this one's different. So there, in this one, they had mad in the middle and then angry on the outer edge. In their belief, angry, hostile, and hurt were just different variants of mad. But here, mad is actually a variant of anger. And if you're suspicious or skeptical, you're angry. Or at least, if you were irritated, someone might say you're angry. And you could probably see that. If someone's irritated, you could maybe see someone saying, well, why are you mad? So, no, I'm not mad. Well, why are you frustrated? No, I'm not frustrated. I'm just irritated. Right? Totally three different words that you can group. Now, if throughout your life, your family and friends didn't use all this vocabulary, but whenever you were experiencing an emotion, they only use those 6 words in the middle, right? Then you might think that that's the only 6 things that you feel. That you either feel angry, scared, surprised, happy, sad, or disgusted. And so when you're feeling some aversion, you might think that that's something that you're disgusted in and not really be able to articulate what it is that you're feeling. If you take it to another level and think about the concepts, if you don't have a concept for something, can you experience it? So if you don't have a clear concept for being ignored and recognizing, you know what, I just feel ignored, then you might think, you might be sad and feel abandoned, right? Which are very different things. When we get back to sight, today's about sight. We can go through as quickly or slowly. What number do you see?
8, 6, 6, 9, 3, 8, 7, 9, 2, 5, 1, 9, 3, 3, 1, 2, 5, 4, 6, 4, 9.
All right. You guys did pretty good. You did pretty good. So you already know that you don't really have to see the number. If you looked at the B in Feldman's book, hopefully I didn't spoil that for anybody. You just had to really kind of figure out that there was a bee in there. Until you figured out that there was a bee in there, you couldn't really see anything. But I challenge you to unsee that bee. So we'll go for all the semester, try not to look at that figure again. Try to look at it later and not see the bee. Basically, you've heard this before. There are certain things that you cannot unsee. Once you've seen it, can't erase it. You've seen this. Presumably, this is the best top-selling poster of all humanity. I don't know if that's true or not, but I can at least see why that could be. So these are the types of things that we use to check our eyesight. This is for spatial resolution. This is for astigmatism. Similarly, you cover one eye and look at it, and then you cover the other eye. And if everything just doesn't look black, if you're seeing some of the lines look gray, then that could mean that your lens in that particular direction is not resolving those lines very well. And so instead of seeing black and white, you see gray because of the shapes, the positions aren't really aligning. All right, so that's how we do it as humans. I didn't show that HSI model today, but we know that basically photons are coming through the air. They're coming in as a sensible energy through layer 1. They're going to receptors. We know now that there's cones and there are rods. And there's 3 different kinds of cones that are mislabeled in some respects, right? Because the red cone really is more sensitive to yellow light than the red light, but it is the only cone that's sensitive to red light because the blue cones and the green cones don't respond, and even the rods don't make it out that far. What else do we know? That goes up through layer 2 and then to layer 3 at the back of the eyeball, which is all those electrical signals that are going to make it up somewhere into your brain. And we think there's a layer 4 and a layer 5 that you don't really have much access to, that automatically is interpreting what you're seeing to decide if the person's saying far or far. Combining that with layer 5 and telling the simulated layer 6 to let you hear in your head the fantasy that the person said far, because they went like, right? And then your consciousness saying they said far, until you look at the other side of the screen and realize that the simulated reality was not an accurate representation of actual reality. So thankfully, artificial devices are actually pretty good. They're not limited to this little sliver of electromagnetic radiation between approximately 400 and 700 nanometers. But you can actually make sensors that are sensitive to X-rays. And because you can do that, you can beam X-rays into people and look at the X-rays coming out the other side of people. Or you can do that to their luggage as it's going through the scanner in the airport. And you don't need to find animals or people that have X-ray vision, right? You can just use technology to help you with that. You can look at gamma rays, you can look at ultraviolet rays, you can look at infrared. If you could see infrared right now, you would be seeing things that were alive and had blood differently than you would be seeing things that weren't alive or had blood. And you would see things that were fabricated to change the temperature of things, changing the temperature of things. Right? You would actually see things flying out of there because what you would be seeing are the cooling at one temperature, and as it goes through away from the air conditioner, you would see it at a different temperature. So it'd be kind of like a waterfall. You would like to see this beautiful waterfall coming out of the air conditioner if you could see temperature, right? And that waterfall would be falling into a room that's roughly the same temperature, except in our room, which would look like a sea, we'd see all these humans bobbing around through through it. So it's important for you to be able to imagine these things. Because if you don't imagine these things, you're likely not going to use the full capability of technology that's available to you when you're creating artificial systems. If we could see radio waves, we'd be very overwhelmed right now because of all the cell phones that are in here. Maybe you could make little glasses for your professors that don't want you using cell phones in class. You know, I don't mind if you use it in class, but then they could put on the glasses and they'd see all the beaming cell phones. Right? How does that work? There's lots of different ways to collect light, but basically it works pretty much like an eyeball. There's a lens. That lens collects the light. It takes it to a photodiode, not a rod or a cone. The photodiode basically converts photons into electrical current. So how do you get color? The most common way to do that is you have filters that are red, green, and blue. And those red, green, and blue filters are spaced very, very close to each other so that your devices, whether they're diodes or they're capacitors are more common now. Whether capacitors, then some of those capacitors are going to be right next to other capacitors that are sensing mostly different color light. Interestingly enough, it's flipped, just like your eyeball. And somehow your camera can figure it out, or maybe not. Have y'all ever tried to do things with the front-facing camera of your phone and not been able to quite figure it out? It's backwards. Do you know it's backwards? I play that trick on people, and a lot of people don't know it's backwards. Take some pictures and see what letters look like when you take pictures of yourself in a selfie. All right, so these pixels, there's really 4 of them that are separated to make 1 pixel. And they're that's so you can have a color camera. Right? Remember, in your camera now, in your phone, you have millions of these things, maybe even tens of millions in some of your phones that are all distinct, and they're measuring different color light. So if you look at one of these super small pixel grids, wherever it is that you hone in, you put a 2x2 square, you're going to find that there's 2 greens and 1 red and 1 blue. So you take your little square, everywhere you go, there's going to be 2 greens, 1 red, and 1 blue. That's called a Bayer pattern. Who wants to take a guess as to why Bayer decided that he would put 2 greens, 1 red, and 1 blue instead of maybe 2 blues, 1 red, and a green? Because we are more sensitive to green. That's exactly right. Yeah, so when there's green light, there doesn't have to be as much green light as there is when there's blue light or red light. So in a way, I'm making sort of a rod, right? It may be hard for me to distinguish the colors when there's not a lot of red and blue, but I can at least see. So it gets a little complicated. There's a number of photons that come in. They're going to go through a filter. They're going to hit a pixel, depending on how long the pixel's collecting charge, because usually we use capacitors now. It's going to create a certain number of electrons. That's going to be discharged from the cell, which is going to create a measurable current. And we're going to digitize that because we're computer people. We don't like analog, we're biased. And we're going to create a number, 42. I just made that number up because 42 is the answer to a lot of life's problems, resulting in a grayscale value. So what can we do with that? Well, we can do all sorts of cool things. We can use that to take pictures of things, like our faces, to unlock our phones. Does anybody actually do that? Use your face to unlock? You do? Image classification, looking for objects. Does anybody use that? I use it all the time because I have like 1.87 billion photos on my phone. And when I want to find something, I just ask Google to find whatever it is I want to find, and it finds all those. Does iPhone do that too?
So you can ask it, search.
I just put air conditioner, and it's going to show me all the pictures that have air conditioning. So, a rainbow, you know, find all the stuff with rainbows.
I noticed like because this one I got like a month ago, and just as I got it, I noticed that it classified the pictures by itself. Like for example, some pictures are classified as portraits, like for example, pictures of a dog, like it's not pictures. It classifies it itself.
So if you have a dog and a cat?
Probably pets.
Pets.
Yeah.
Very cool. So it's you can also search by images. Google has this right built into the phone. I love it. Basically, whatever I see, if I just take a picture of it, and then if I want to buy it, like it'll take me to the sites where I can buy it, or it'll take me to other things that look like it or explain it to me. If you haven't done that, that's pretty cool. I imagine iPhone has some things like that, but I don't have an iPhone, so I don't know. Medical diagnostics, image processing, lots of things you can do with images. You can do a lot of things with sound too, but there's something about sound that's different than images, and that is that sound, so you can't see sound. Right? There is something about spatial resolution to sound and temporal resolution to sound, because you can tell when there's echoes, right? If you work hard in training, you can kind of tell where a sound is coming from. So you can do a little bit more, but definitely not as sophisticated in terms of what you can do with your eyesight, right? In terms of seeing, identifying things, and orienting yourself. This is a company that I founded actually in 2009 from work that I started at University of Texas Southwestern Medical Center in 2007. If you're curious, you can look it up on LinkedIn. I did a post on it about a month ago. What this company does is it uses a unique imaging head, basically, we created to pulse light into the body. And then it looks at the light that's coming out of the body and collects it on a sensor, kind of like the sensor that would be on your camera, kind of like a video camera. The difference is when the light goes into your body and it comes back out of your body, and this is just regular light, basically, like red light mostly. When it comes out of your body, it's actually been modulated. In other words, if you just take constant light, like a flashlight, and pump it in, and you were able to see the light that comes coming out, you're going to see the light's going to be varying in intensity like this, roughly. Do you know why that might be? Huh? Because of the pulse, yeah. As your heart's pumping blood through your body, the distribution channels are varying in size because it's not a constant flow. And as it does that, there's going to be more or less oxygenated blood at any given point, and that varies as your heart is beating at that rate. So you can actually look into the body with regular light, even though you would think that light doesn't go through your body because you can see the top part of my body, right? But who here thinks light goes through the body? does? So it does, right? We just don't think about it because most of the light that's bouncing off of you is coming right back off. So that's so much light that your eye can't see the light that's actually going into your body and coming out, which is happening right now, or the light that's going through your body. Right? So you constantly have light going through your body. It's just because you don't have that much light going through your body, you can't really see the light coming out the other side unless I do something like this. Right? You can try this at home. So it's true. All right. We did pretty good. Do you feel like you've learned a lot about light? Are you enlightened? Okay, we've talked about humans, how light comes in, but it's really upside down, but your super cool brain flips it. And we learned, thanks for sharing, that if you were to put on some cool glasses that flip the world, eventually you would compensate for that. I don't recommend doing that at home. We learned that technology gives you the ability to look way, way beyond the range that you can with your eyes. And that if we imagine what it would be like if we could see that way, then we can start envisioning, conceiving of, designing, and implementing systems that are super intelligent, right? More than artificial general intelligence, more because they would have, greater access to the information of the real reality that's around us. And we remember from the class a few weeks ago that we don't have to just let our robots benefit from that. We can also use augmented reality, right? So that we have glasses that maybe do let us see a little bit of electromagnetic radiation, at least enough to see, if there's a cell phone in the room that's on. Maybe it's your own cell phone, you can't find it, you put it on silent, it's not vibrating, and you want to find it, right? So that could work too. Any questions about sight? Yeah. All this stuff is going to be on Moodle. So a rose by any other name would smell as sweet. Would Lisa Feldman agree with that? I don't think so. All right, you should read chapter 3. Not just because this said so, but because I think you're going to enjoy reading more of her book. And because it's going to be subject material of the exam, the first exam. You're not going to have another homework before the first exam. Yes, and the introduction. Plus everything else that you've learned in class and been on your homework, with the exception of you're not going to be programming on the exam. This is not a programming class. This is a class that's intended to help you know what to program and how to program it. I would suggest that you understand at least what it was you were doing there. You should know what libraries are and that they're artificial deep learning libraries and that kind of stuff. So you're not going to be programming on the exam. The purpose of the programming is that later on in the class, we're going to be doing a project report. And to the extent that you understood the programming, it will help you do your project report. Oh, look at all this. Homework number 3 is available on Moodle. It's due this Wednesday at noon. There's no class and there are no office hours on Wednesday because my meeting in San Juan starts at 7:30 in the morning. If you have any questions, so I will have office hours tomorrow morning at 8:08 a.m. Feel free to post questions on Piazza and help each other, or wait for me to get to them. Exam number 1, we are going to have one more class before the exam, but just so you can keep this in mind, it's going to be on March 9th, the Monday. We're only having one more class because I'm not here on Wednesday in San Juan. Monday's a holiday. Then we'll have the class on Wednesday. Then the next Monday is the exam. Bring pencils. Normally there's an online portion. If there's going to be an online portion, it'll be available before midnight on Thursday, March 5th. I like the online portions because when I do the online portions, it usually helps in the class. Basically, you're not usually worried about time. It usually doesn't take that long to do the in-class portion. Material related to everything covered in classes, homeworks, middle course page, and required reading assigned prior to the date of the exam. Usually if you've gone through the slides and the recordings, posted questions on Piazza, or come by my office hours, you're going to do well on the exam. And especially if you know how to model something. And if you don't, come see me before the exam. Basically, the kinds of questions that we did on the first homework, where you had some scenario like a professor, and you had to create a model, label that model, and explain it. I would be surprised if there wasn't something like that on the exam. I haven't made the exam yet, but I'll be surprised if there isn't something like that on the exam. All right. So eyes and ears have a lot in common. This list was actually put together courtesy of last year's class. They both have inputs through a physical organ. Both output electrical signals for further brain processing. Both have ranges which we can sense and can interpret. Both are characterized by intensities and frequencies. Distinct portions of each are sensitive to different aspects. How are they different? Well, when we're talking about hearing, we're talking about forces. Remember, there's 5 sensible energies. Forces is one of them, because these are vibrations in the air. Sound can traverse opaque objects. But I can't see through this opaque object. I can see through this opaque object. If I shine enough light through it. In air, sounds are waves. Light is waves and particles. This is because we don't really think about sound as a particle in air, but you can think of sound as a particle in some solids and liquids, if those solids and liquids have regular forms. Those are called phonons. Bless you. Sound is slow and light is fast. But we all know that light is not so fast that we can actually know what's happening to a star today. If we wanted to know if all our stars were great, we would have to wait years and if not lifetimes to know that. But we can't go look at a star and see what it looks like today. We can look at the sun and see what it looked like some period in the past. The sun is actually also far enough away we can't see what it looks like instantaneously. Question? Yeah. Definitely you cannot see it now, and I don't suggest you look at it. But there is a delay, but it's not that big a delay. Jesus says it's 8 minutes. Yes. Correct. So you can see in the past. That's all of our superpowers. All of our superpowers at night when we look at the stars, we're looking at the past. Hearing and seeing kind of go together. We saw it in the McGurk effect. We see there's a lot of similarities associated with them. In every case, the reality of these vibrations and the reality of these electromagnetic radiations or photons don't get into our heads. Right? As far as they make it to is into the eye or into the cochlea, where they're converted into electrical signals that then your brain interprets and creates a simulated reality for you. That's why I love eyes and ears, because they're physics. For me, I like physics. There are a limited number of variables. They follow these equations, actually. Einstein had a lot to say about some of those equations. There's a one-to-one relationship. Equations are known. Physical phenomenon transduces into electrical signals. You have microphones that pretty much work like cochleas, and you have cameras that pretty much work like your eyes. And you can see a lot of information, and even though it's not instantaneous, it's reasonably close. Right? If we're hearing someone in the room, even though you're not, the vibrations I'm causing aren't going into your ear instantaneously, right? They're traveling at 343 meters per second. Unless you're 343 meters away, you're going to hear it in less than a second. Smelling and tasting is a totally different story. There's a video. I'm not going to play it in class because we're going to gain minutes, but whatever's in the video could be on your exam. So the link's there. It's a fairly short video made by the Khan Academy, which coincidentally, one of the boards of directors and investors in that company was my very first intern. My very first summer intern at TI when I went to work there, was one of the guys behind this company, Khan Academy. Observations of taste. We sense molecules transported to taste buds receptors on our tongue. The tongue's thousands of taste buds have a disputed number of distinct types of receptors. That's because someone decided that our receptors, and this is why I love biology, we were going to call them sweet, savory, sour, salty, and bitter. The interaction of those receptors with the target molecules results in electrical signals that our brain interprets as, ooh, that's yucky, or isn't that awesome? Right? Is there anybody here that thinks that freshly baked chocolate chip cookies are yucky? Right? It's a total legitimately thing to think. You do?
Yeah, for example, I get a little bit disgusted with sweets because if I eat a lot, at some point I get
Over. So maybe you have a lot of taste buds. Or maybe your taste buds are very, very sensitive and they're being overwhelmed. Do you think you could retrain yourself to like something that you don't like?
When I was a kid, I used to eat a lot of sweets. I even put sugar on my Jeff Weir beans and everything. I ate a lot of sugar, okay? And all of a sudden, I stopped liking sweet stuff. I discussed, cake, donuts, pastries, sour candy, something like that.
I'll make a note. So last year's final exam, I brought Krispy Kreme donuts to the exam. So I'm not going to lie. So I actually, because I have been doing this now for several years, I constantly look for ways of understanding myself better, which means I constantly challenge myself in different things to see like how my brain works through those challenges. So one of the things I decided I was going to do was that I wasn't going to put sugar in my coffee. Now, living in Puerto Rico, you know, having parents that are Puerto Rican, café con leche means sugar. Like the coffee and the milk are extras, right? Basically, it's an excuse for sugar. Your brain's a pretty amazing thing. Now, when it really likes something like café con leche, it might take you a good part of a year. But at some point, you're really just going to get used to it like you got used to that color thing at the bottom of the screen. So why did I do that? I did that because later on in the course, you're going to learn about brain chemistry and how important brain chemistry is. And I was fooling my brain by giving it artificial sweeteners. And I just decided that I didn't really want to fool my brain, that I wanted my brain to not be fooled. I'm not saying they're good or bad for you, but I just decided I didn't want my brain fooled by artificial sweeteners, so I just got rid of it altogether. So you can also do these types of things to help yourself understand yourself better, give you challenges, and observe how your brain seemingly may work against you for those challenges. Yes?
I did that just for fun when I was since I cook my food. I started cooking the meat without any salt at all. It was at first it was like it didn't taste like anything. It was just like the vibration and sound and how it felt, but it didn't taste like anything at all, like nothing. Like I had just water in my mouth. But right now I can just eat it like this. I don't mind. I don't like it because I like salt, but I don't mind if I can eat it like that. And I can also eat it with really low salt, and I can feel the salt. And that's one thing that I can do back then.
So that's you know, and so the reason we go through all the senses is because some of our senses are easier to like relate to, right? And you can do these types of things and see that you can actually reprogram your brain, right? Some of the types of things that we sense and interpret, like emotions, which is what Dr. Feldman talks about, are a lot less crisp, if you will, than, you know, light, the color of something, or what something sounds like. But I'm going to suggest to you that you can also do the same thing there, even though it might require a little bit more effort. So how taste sensing really works is still being determined. Receptors are classified based on what is perceived versus what is measured. We sense molecules we talked about on the taste buds. One thing I will tell you, I'm sorry, and then it's actually in the English language. I don't know if this is true in the Spanish language, but there's an association with these taste buds and emotions. So things that are sweet are supposed to be like happy. And things that are sour are supposed to be more like sad or bitter. If you're bitter about something, it means that you're angry, but we already know it doesn't really mean you're angry. That's just a generalization of the word bitter. It just means that you're bitter. They do tests to see how sensitive you are, right? These are going to vary. Some people are going to be more sensitive than other people, and that can change over your lifetime. Broccoli, I really never liked it, and now I really actually kind of dislike it less. But it's amazing. Look at this molecule. You can barely with your eyes tell the difference of it, and it's amplified. It's literally like one little difference. But the one on the left, you would taste as sweet, and the one on the right, you would taste as bitter. So this is just going through different ways that scientists test people's taste buds. This is an artificial taste receptor. This is actually my first ever invention. I like to throw things into the class. That little device there in the middle was my first invention when I worked at Texas Instruments. And the way it worked is we actually put biomolecules on the surface of this device here, and then you run liquids over it, and then the molecules that were in it would bind to the surface, and that would cause a change in this surface plasma that we would detect with the light that was inside. So we used to call that. Sprita still exists. It's used now mostly in research labs to do like drug target analysis. It's not used for taste, but at the time we were using it to look at food. There's another thing on smelling, con and smelling. So watch that video too. I think you'll like the videos. They like draw things and stuff. By the way, tasting and smelling go together. So that's why if you're sick and things don't taste well, you could also do it like this. Try to go like that. It tasted, things are going to taste the same. So there's a collaboration. Where have we heard about collaborations in senses before? So there's like a McGurk effect of taste, right? She talks about it in her book, actually. I don't remember what chapter. Did you get to the diaper with chocolate? Yeah. Okay. So that's like the McGurk effect, right? In a way. Right? So you could actually create a sensation of a smell in your brain. Because remember, those bottom molecules aren't getting to your brain. They're stopping at the taste bud, right? But they're also being smelled, and you're also looking. So there's some cool McGurk-like effect between taste, smell, eyesight, and your preconception that if it's brown and on a diaper, it's not going to smell good. So do you think those people actually smelled something fantastic and just thought it was something else? Or do you think in their brains they heard bar when there wasn't far, or they smelled something bad? So they actually smelled, the simulated reality of that smell was bad. It wasn't that they smelled something good and their consciousness thought it was bad. So just like the taste, the smell receptors also can distinguish things that otherwise look pretty similar. This is spearmint and caraway. Supposedly we can distinguish, I don't know how they counted this, but a number I can't even, is that trillion? Is that trillion?
Yeah.
Okay. A trillion cents. Trillion cents. It's a lot of cents. $10 billion worth of cents. Those little jokes. Different kind of cents. But we don't have a trillion names for cents. So just like the emotions, just like the colors, our language is very, very limited. Right? We feel all sorts of things, but we don't really tend to do a good job. Some people do. Some of you might do it, but most people don't do a really good job of assigning words to what that distinguishes, or to the colors. Right? To me, it's blue. They're all blue. When you put them next to each other, sure, one of them is lighter than the other, but when you put them alone, to me, they're blue. I'm not going to be telling you they're, you know, rustic ocean blue. Those words aren't coming out of my mouth. And there are artificial smell detectors too. Similar to what I showed you with the Sprita, except these work with air, basically. And there's arrays, just like pixels, and they put lots of different combinations of chemicals with the idea that some chemicals will interact. And this is actually like AI defined, right? Because if you had one molecule coming and touching one taste bud, you're probably not going to have a very crisp sensation of any sort of taste, and the same with the smell. So it's the combination of things that you're sensing and interpreting with your brain. So these are arrays that go into sensors, processors use it, and that's why if you go through the airport, sometimes you'll see like they'll swab your thing, throw it into a machine. It actually works in a slightly different way, but they're looking for smells. They're looking for the chemical composition of what you have. Certain combinations of that can lead to you getting stuck at the airport. So we actually got through sight, taste, and smell. And we're on time. Any questions? Hopefully, and maybe even more so than if I had split it up into 2 classes, you're able to see similarities between these senses, and you're able to see difference between these senses. But hopefully you're starting to see that what Feldman's talking about in her book when it comes to internal feelings and concepts that you're applying, just like she suggests in the book, isn't really all that far removed from what we do in our brains when we're interpreting where it's coming through our eyes, through our ears, through our mouths, and through our noses. Thanks.